Hi everybody, my name is James Ehlers, and today I'll be presenting my DFMA changes to the Nutcracker project. So the original design of the Nutcracker, it featured different components that were assembled together to create the final product, and the vast majority of these components were machined. They were manufactured on site, and they were made out of 304 stainless steel, while a few of the other components were simply just ordered from McMaster-Carr and were made from galvanized steel. And these common operations for machining these components included sawing, lathing, milling, drilling, reaming, and grinding. And then on the plated parts, such as the brackets and covers, they were sent out to a third party to be water jet cut. So the drawbacks for manufacturing in the current state, first off is the material selection. As I mentioned earlier, 304 stainless was used on the majority of these components. And stainless steel, it performs great. It's extremely strong and it has a great corrosion resistance. But for the Nutcracker application, it's too heavy, it's expensive to order, and it has a very poor machinability. And then next up, how it's machined. I noticed there was constant tool changes and excessive time grinding the components to reach a desired surface finish or to reach a tight tolerance. And then finally, how the Nutcracker was assembled. I noticed there was a wide variety of different part types. And so my alternative solutions for the material selection would be to get rid of using stainless steel entirely and to instead use 6061 aluminum and polypropylene as the new materials. And these are cheaper investments due to the much better machinability and lower density as shown in the chart below on the left. And the machinability would lead to less tool wear, having a better machinability. As you can see, the aluminum being at 270% versus 45%, that tool life is going to last a lot longer than if the bits were cutting through the stainless steel. And to go along with that, the density would greatly affect the component weight and ultimately the product weight of the Nutcracker. And I decided to use aluminum on the drive shaft, crushing wheel, and crushing pin because these components were constantly going to be under stress and exerting force on the nuts, whereas the covers and brackets, they were more so for housing and working as a shell for the product, so the material didn't have to be as strong. So polypropylene, although it's a strong plastic, it's obviously not as strong as the aluminum, but it's much lighter and it's going to be easier to manufacture. So next up, the alternatives in manufacturing. As I mentioned in the last slide, the brackets and covers will be made from polypropylene, and to make this happen, they would be sent out to a third party to be injection molded. And next up, I would fillet the edges instead of having these straight jagged edges to reduce or even eliminate the grinding operations. So this would be done in the design stage. So I provided a screenshot below of the grinding wheel. As you can see, those V-shaped cutouts, they would be changed from having that V shape to having a filleted edge on each corner to have a smoother surface finish to ultimately prevent the nesting and sharp jagged edges from occurring. So this would greatly reduce or even eliminate the need for all that excessive grinding. And then finally, I would order smaller sized raw material to limit the use of having to lathe down the raw material to get it to be the correct component size. And so finally, the alternative solutions in the assembly, I would start by standardizing the geometry on both the right and return brackets to have the entrance point and the exit slot be aligned, and this would ultimately make the part geometries identical to one another and this would be to simplify the inventory and to limit the confusion for the assemblers so that they wouldn't accidentally place a component where it shouldn't be placed. And so next up, I would tweak the design of the drive shaft and crushing wheel so that they would be machined as one piece instead of having to be made separately. And then on the current state, too, to make that work, it was fastened by a tight press fit, which it functioned fine, but just the whole concept of machining it to have such a tight tolerance to have that press fit, it's a bit unnecessary, and this could easily be avoided by just combining the parts. And this would work because the parts do not have to separate at all. They don't move relative to one another, and they're made from the same material, which is that 6061 aluminum. And finally, I would standardize the size of the bearings ordered. So instead of using the 1.5 and 2 trade size bearings, I would use both of them to be the 2 trade size. And because there's that 1/2 step up on the bearing size, that would also cause the crushing pin and the bracket hole call out to be, they would have to increase by 1/2 inch as well, which could easily be changed in the design stage. And so a quick summary and second for open questions. I provided a chart which shows the total calculated weight that I got from estimating the volume of each component from the process sheets and multiplying that volume by the provided densities of these different materials. So as you can see, I was able to get the final product weight to be under the 30-pound threshold of these manufactured components. And some open questions that I was a bit unsure about that I might not be able to answer were just getting an accurate total cost of everything. And so, for example, I mentioned how these plastic components, they would be sent out to a third party to be injection molded, and I could assume that the injection molding process cycle time would be 2 minutes per component, but I'm unaware of the cost of labor, the whole logistics of what it costs to ship back and forth, and how long the lead time is, that sort of thing, because that ultimately affects the total cost of manufacturing it. But other than that, this was these were my methods that I chose to improve the design and manufacturing of the Nutcracker, and these were ultimately to improve the cycle times, to reduce the weight, and to limit the amount of operations needed to manufacture this Nutcracker. Thank you.